What if building a time machine wasn't science fiction? What if physics already gave us a real way to travel through time? Before we build anything, we need to understand one strange fact. Time does not pass at exactly the same rate for everyone. Einstein showed that motion and gravity can change how time passes. This means time itself is part of our physical universe. Let's start with two identical precision clocks. If everything is equal, both clocks should tick at exactly the same rate. Now we move one clock extremely fast while leaving the other behind. According to relativity, something very surprising should happen. When we compare them again, the clocks no longer agree perfectly. The difference is tiny, but it is completely real and measurable. This is called time dilation, and unlike science fiction, scientists have actually measured it using incredibly precise atomic clocks in laboratories. So our first time machine is not really a machine. It is an experiment proving that time can genuinely pass differently. Now let's make the effect much stronger. Our next idea is simple. Build a spacecraft and make it incredibly fast. At ordinary speeds, relativistic effects are tiny, but as our spacecraft approaches light speed, the difference becomes dramatically larger and more noticeable. Imagine the ship reaching half the speed of light. The astronaut's clock would begin running slower relative to clocks on Earth. Now increase the speed to 90% of light speed. The effect becomes much stronger, and our journey starts getting very strange. At 99% of light speed, time for the traveler passes much more slowly compared with someone who stays on Earth. This gives us a real time machine concept. Travel extremely fast, return home, and discover that more time passed on Earth. The astronaut might experience only a few years, while decades pass for everyone who remained behind. That's genuine travel into the future. And this is not just theoretical. Relativistic time differences are measured in real technology, including the timing systems used by GPS. Now we have our first real design, a relativistic spacecraft with propulsion, navigation, life support, and extremely precise atomic clocks. The spacecraft leaves Earth, accelerates to an enormous fraction of light speed, travels for years, and eventually turns back toward home. Inside the ship, the astronaut experiences much less elapsed time than people waiting on Earth. When the ship returns, Earth is older. The astronaut steps outside and discovers a world decades ahead. No magic portal was needed. Physics itself created the time jump. But there is a massive problem. Getting a human spacecraft anywhere near light speed requires an enormous amount of energy. As velocity approaches the speed of light, accelerating a massive object becomes increasingly difficult. Our engines simply are not powerful enough. Then there are radiation, collisions with tiny particles, heat, shielding, navigation, and keeping humans alive during such an extreme journey. Our theoretical time machine works according to known physics. The problem is not the equation. The real problem is engineering it. So let's try another route. Instead of moving incredibly fast, what if we use something incredibly massive, gravity itself, at extreme strength? General relativity tells us that stronger gravitational fields can make clocks run slower relative to clocks farther away from them. That means an extreme gravitational environment could create a huge difference between the time experienced by us and someone far away. The most extreme example we know is a black hole, where space-time becomes dramatically curved by enormous gravity around it. Our spacecraft approaches the black hole carefully. The closer it gets, the stronger the gravitational time dilation becomes around the ship. From far away, observers could see our clock running much slower. For the traveler, however, local time would still feel normal. But there is a terrifying problem. Getting close enough to a black hole creates extreme gravitational forces and potentially lethal radiation. So using a black hole as a practical time machine is currently impossible. But it gives us another important clue about space-time. Now imagine we could manipulate space-time itself. Instead of crossing a huge distance, what if we created a shortcut through space? That idea is called a wormhole. a hypothetical tunnel connecting distant regions of space-time through a much shorter path between them. In theory, a spacecraft could enter one opening and emerge from the other, crossing an enormous distance almost instantly through space-time. But creating a stable, human-sized, traversable wormhole is far beyond current technology. We have never built or observed one directly. Some theoretical models require unusual energy conditions, including negative energy densities, to keep a large, traversable